So momentum we discussed was a product of mass and velocity. So how much momentum something has depends upon two things, like how fast it's going, which is v, and also what its mass is. So the product of mass and velocity, mass times velocity, gives you your value of momentum for that particular object. And all objects that are moving, you know, they might collide with something else, they might be travelling on their own, they have an associated momentum with them. And that momentum is measured in kilograms meters per second. That comes from the units for mass, which is kilograms, and the units for velocity, which is meters per second. So kilogram meters per second. If we want to figure out the momentum of just one individual object, then we use this equation. We use the letter P for momentum because M was already taken. So P equals mv for one individual object. That's dead easy. It's just a simple 3-variable calculation. It doesn't get any more complicated than that for one object. But at a higher level, what we're mostly looking at is two objects colliding. So we have to consider the momentum both before the collision and after the collision as well. So we started off with an example of a car that is travelling with speed and collides with and sticks to a vehicle that is stationary. So as with our dynamics calculations, we draw out a diagram, we draw out a free body diagram to show all the information that we know. We don't have as much complicated stuff as we do with dynamics calculations. We've only got a few speeds. At this stage they're all going in the same direction. We've got same masses, you know, drawing things in a box and writing the mass within it. But we had to distinguish between both before and after the collision. So we decided that we would write our stuff from before the collision on the left hand side and our stuff from after the collision on the right hand side. So we've got one object here moving with a speed of 5 meters per second as per the example. This one is stationary. Afterwards they stick together and they move off with a common velocity, which we will calculate in a minute as being 2. But we needed to also distinguish between this mass and this mass, this speed and this speed. So we decided that this would be m1 and that this would be m2. Same goes for after the collision as well. And we also decided that they would have different speeds. So initial speed we use u, so we decided this would be u1, this would be u2, this would be v1 and this would be v2. v1 and v2 are the same here, they're equal to each other because they're both moving off with a common velocity. But just for argument's sake we labelled them as so. So that allows us to not get confused between which speed is which and which mass is which. We then apply what we call conservation of momentum. Now all objects, when they interact with each other, obey conservation of momentum, which basically means the amount of momentum you have at the start is the same as the amount of momentum you have at the end. Much like conservation of energy, you must have the same amount of momentum at the end as you go in with. So we apply that to this momentum collision. We say that the momentum before must be the same as the momentum afterwards. We already know that P is equal to mv. That's our momentum of one individual object. Momentum is the product of mass times velocity. So all we do here is apply that equation to each of the individual masses with each of their individual velocities. And if we do that, we come out with this complicated looking equation here. Now you won't be given that in the data booklet, you'll be given this in the data booklet, that's the only equation you'll get. You've got to be able to extend that to look like this. So that's your momentum of this object before the collision, that's the momentum of this object before the collision. Add them both together, you get your total momentum before the collision. Afterwards, that's the momentum of that object after the collision, that's the momentum of that object after the collision. Add them both together, you get your total momentum after. So it's just a case after that of plugging in the numbers. What we did there, instead of treating them as two separate momentums, we just added the masses together and multiplied them by a common velocity. And then we solved for the answer, which we decided was 2 meters per second. So in every momentum calculation, and in the experiment in a moment, what we're going to do is just draw out a diagram like this, indicate on it what the masses are, what the velocities are, and then we can figure out what a missing velocity is, or even a missing mass as well, as you sometimes might be asked.